All right, and so now at this point we are ready to step into the next form of an improper integral right there. So we have seen earlier throughout our example 1 and throughout our introductory problems earlier that, so we've had this one in the beginning that, and we now know how to handle that. So say for a function e to the x right here, okay, and then we took that definite integral from 0 to, and actually here how about e to the minus x, if I recall that correctly from our introductory problem, and then raise that to we are taking integration from 0 to the infinite upper end right here on the function e to the minus x. And then we also investigated the function, say, e to the x, okay? And then our interval of integration went from minus infinity to 1. Okay. And so now we have learned how to investigate, if we have investigated these two forms. So the third form I'm introducing now is that, so what about on a function, just e to the x, okay, e to the x. I want to find the integral where the integral limits are from minus infinity to positive infinity. Okay, and this is where it's becoming dangerous for the problem in a sense that none of the limits here of the integral problem is a finite value. Okay, the bottom limits of this integral problem is an infinite value, negative infinity, and the upper limits of this definite integral is also an infinite value, a positive infinity. Okay, and so generally speaking, this brings us into the third form of an improper integral. Let's say on a function being continuous on the interval at least from negative infinity to infinity, then on the interval continuous on the interval from infinity, negative infinity to infinity, then we're accumulating from minus infinity to positive infinity on that function. And so yes, let's consider our function be f of x is continuous on that interval from minus infinity to positive infinity. So that's the third form of the improper integral that we are heading into and investigating those. Okay, and so what's good about, what's waiting behind, what's waiting for us here when we're getting into investigating these problems? So let's find out. Okay, so with this particular problem that I'm promoting here, so the idea now is that as the plan here, I am going to actually produce you see, so this interval, this overall interval from minus infinity to infinity is pretty much the whole line of real values. The whole line of real values. And so in that way, in the entire line of real values, negative infinity to infinity, and our function here is a continuous function in this entire real domain, real line of the entire line of real values right here, then we can just simply pick a c value somewhere. It doesn't have to be exactly in the middle, because where is the middle of this whole line of all real values? So we just simply pick a c, a value c. And so this value c now, that's once we have picked, it is now a finite value. Okay, so here's how I'm seeing it. So the same function here, the function can be, and now everybody knows the e to the x, but I'm just saying, arbitrarily, or in generally as any function with a curve that's, spreading throughout the entire line of real values, then from minus infinity to c, on this function f of x right here, we can produce as a plan right here, that's function that we're having, but we can do accumulation from minus infinity to this finite c value that we chose. Okay, and then we can consider a separate interval from c, accumulating from c the finite value to positive infinity on this same function. Okay, and so that c value can be a 0, can be a 1. So now specifically, let's apply that idea, okay, into our particular case here, being the e to the x function. So how about e to the x function? E to the x function, but I'm considering separately as two separate improper integrals. And now let's And like I said, 0 or 1 or 2, it's just a value that we can choose. So here I'm going with 0. Okay. Now we can just simply produce for ourselves two separate problems. Okay. And then we're going to consider the two answers here, to consider the two limit calculations here. So each one of these will definitely give us a limit problem. And then we're going to consider the two limit problems here separately. Okay? And then now once the answer, the final answer on both, once each one of these arrive upon a finite value. So again, what I'm saying, once each one of these arrives at a finite value, then the final answer here can be simply the summing up of these two. Okay? Of the two separate improper integrals. So this is in form of this is the form A that we've learned previously, and this is form B that we've learned previously. But now, as soon as both of these, okay, or once we've proven that both of these all came to successful finite values, then this overall answer will be the sum of these two. Okay, and so of course the function e to the x is that curve that's spreading that way throughout the entire line of real values. So now we're gonna have to apply the technique on each one of these. Okay, and so now with this problem, allow me to hold on to that problem. And let's get into considering the two separate limits right here. So now on the e to the x, that we're accumulating from 0 to positive infinity. Okay? Because this one here is the interval from 0 to positive infinity, which is the positive interval and including 0. So a lot of times, naturally, people would start out with that one first, and that would be the same case with me here. So now in that way, just like how we've learned through the earlier examples and through the earlier discussion, that this problem here, we can consider a separate limit problem from 0 to t, an arbitrary, finite, definite integral on the function e to the x over that interval from 0 to t. But now we need to be letting t approaching positive infinity. Okay? And so this work here, fundamental theorem of calculus, now tells us that the antiderivative here needs to be e to the x, and on top of that we are going to evaluate our antiderivative at these two limit values here, integral limit values. But then we have to, at the end, evaluate the problem as a limit problem, letting t to infinity. So just like how we've done that in the earlier examples. And so now this is e to the t minus e to the 0. And then, yes, definitely we consequently ran into an expression in terms of t, and we take the limit as t approaches positive infinity. So this answer here gives us and that term here, that term e to the 0 is a 1, but the overall expression here will give us a positive infinity. So this particular limit here diverge. Okay? So this particular improper integral here is divergent. So one of them is divergent. So that means actually, now, in case anybody would like to know, then I will also mention on my other board here, the same function, but on that interval from minus infinity to 0. With this improper integral, it's a form B that we have seen earlier. Okay, then we can produce separately as a limit problem, letting t to negative infinity, but we're setting up from t to 0 on this e to the x function. And then this will consequently produce for us, and quickly the work here, e to the x as the antiderivative, and then t evaluated at t to 0, and then we need to be taking the limits, letting t approaching negative infinity. And so in that way, in the next step, I'm looking at e to the 0 minus e to the t. And this is consequently an expression in terms of t, just like how we've seen it throughout all of our example problems previously. And now I'm taking the limits as allowing t to grow to negative infinity. And so in that way, what I see now is that this particular limit right here, in case anyone start out with considering this improper integral first, because remember, we need to consider two separate ones. One of them is this one, the other one was the one I carried out, I worked through on the other board right there. But so, in case anybody worked out with this integral first, you will find out that you will run into a finite limit. This term, as t goes to negative infinity, will go to 0. And this term remains a 1. E to the 0 is a 1. And so, in other words, in this problem here, according to the logic we have seen earlier, in this problem here, this improper integral on its own is a convergent one. Okay, this one here is convergent, and that implies that we have an answer for this one here. The improper integral from minus infinity to 0 on the function e to the x is equal 1. But then, even if you started out with this case right here, now that combined with the other ones that I've had here, now I started out with this one first, and I found it divergent. But like I said, in case anybody found the other piece of integral first and found it successful, you still need to advance to the other one and make sure it's also a finite value. And that's what I'm trying to express right here. Okay, so now two separate improper integrals, but one of them failed, one of them is divergent right here. And I actually started out with this one first, and I immediately found out that this one here is already divergent. So that means my overall here is the ultimate conclusion. And so now, upon realizing that one of my two pieces of the improper integrals is a divergent one, so now my overall integral on the function e to the x from integrating over from minus infinity to infinity, this improper integral here, the third form that we're currently learning, is divergent. And so now, in a similar logic that I have pointed out, so as soon as we arrive at saying this one here is divergent, we don't need to write what it's equal to. We just say that it's a divergent one, and we don't need to worry about what's that final answer, because there isn't. Okay, it's just a divergent one. Okay, all right, so now at this point we started getting a good hang of that. So the main idea now is that anytime we're looking to this kind of problem, a function supposedly continuous over the entire line of real numbers, then integrating over that interval from minus infinity to infinity, we have to start out as a plan right here. We start breaking it down into two separate integral. Okay, one of them is an integral from minus infinity to c, and another one is c to positive infinity on the function here. Okay, and then as soon as we can verify, which we already found in this case right here, one of our two improper integrals here fail to be convergent or being divergent specifically. But if in any case that you reach both of these being convergent, then we can just simply add the two answers here, and that will equal to our work, to our overall improper integral as stated in the beginning here. Okay, and so that's the plan for how to handle these kind of problems. And so now we are ready for getting into an actual definition of what it means by being this third form right here of an indefinite integral. And I believe I said the indefinite integral, but what I meant here was the improper integral. Okay, all right. So now as a definition again. And again, allow me to be skipping some minor details in my wording of this particular definition here compared to the way how it's worded in many standard calculus textbooks. So as another definition, okay, then so here I have to say clearly, if both, or anytime we reach to both improper integrals, the one minus infinity to c on this function, on a function, and the one from c to positive infinity, if both of those are convergent, okay, if both of these are convergent, then we define, then the way to do this one, then the way to evaluate this minus infinity to infinity integral on the function f of x is going to be just simply the sum of the two improper integrals results together. All right, and so this definition again sort of defines a way how to handle, or it defines what it means by anytime seeing an integral where we're accumulating over an infinite interval like this. It's a completely infinite interval. It's from minus infinity to positive infinity like that. Okay, and then in that case, this integral is set set, and that integral is set to be convergent. All right, and then otherwise, that means when we fail either one of these, once we fail any one of these to be a convergent ones, then that's what it means by otherwise. Then that integral from minus infinity to infinity on the function, okay, is said to be, and the term here again, divergent. All right. Okay, and so now after seeing this definition, and again, forgive me that I skipped out some minor details in the wording compared to the actual wording in many standard calculus textbooks for this. But this wording here should be giving enough understanding for how we can tackle down this kind of improper integral right here. And so again, it's strictly important to understand that we have to, so anytime you are given a problem like this, we have to first start out considering two separate improper integrals. There are two separate improper integrals to handle, okay? And then once we have reached both of them, once we have found out that both of them are convergent, then we can say that the answer to this problem right here is the sum of the two separate problems here, okay? And I mentioned this, and now we're gonna get started into example 2 right here, where we're gonna start seeing how any of these, and along the way, we're gonna see how any of these will work, okay? The process to get these problems done, and along the way, I should be able to point out some more logical understanding about the problems, about the steps. All right. All right. So now let's look into example 2. And again, example 2 is intended to be exactly the same kind of instruction I've given back in example 1. So here's the wording of example 2. I want to determine whether or not the integral given is convergent or divergent. So we want, that's the first part, we want to decide that first anytime we're given an integral. And then once we know it's convergent, if it's convergent, okay, then we're gonna evaluate the integral. All right, so that's the main. So again, just like the logical thinking and as a thought process, how we've done through example 1, the first thing in any of these improper integrals is that we have to decide whether it's convergent or not. If it's convergent, then we're going to proceed further to find its final numerical value. That's what it means by evaluate. Otherwise, as long as we can prove that it's a divergent one, then we stop right there by making that final conclusion. The integral, the improper integral, is divergent. Okay, that's all it needs to be, and we don't need to find because there isn't. So in that case, we don't need to find any final numerical outcome, numerical value at all. Okay, so now let's get started with our first problem here in this example. So part A of the example here. Let's look at the integral for an integral from minus infinity to positive infinity on the function. How about minus 7x squared plus 6x plus 4, okay, dx. All right, and so now on this function, again, now allow me to go with the way how many textbooks writing it a little bit, and then at some point I'm going to depart and separate out into my own way of delivering this to people. Okay, but so I see it's fine that many textbooks start out writing this integral is equal to, sort of like it's not exactly equal, because at this point logically we don't know if it's equal yet, because we still don't know how to verify the two, but it's sort of like a plan. Okay, the plan here is that we want this integral from minus infinity to equal the sum of and we can choose a point 0. This function is a polynomial of degree 2, right? So it should be a continuous function, and so we can just choose, I choose 0 here. So how about I break it down to minus infinity to 0 on this function, minus 7x squared plus 6x plus 4. So we want this integral to open to be equal to the sum of that integral and another sum, and another improper integral from 0 to positive infinity on the same function. So minus 7x squared plus 6x plus 4. So tentatively, or as a plan, we want that to equal the sum of these two. And these two are now quite familiar with any one of us at this point watching this video lesson, this video lecture over here. Okay, and so from this point on, now we should not make more equal sign and then equals, and then the first one here is one problem and the next one here is one problem. Let's kind of put a pause here and consider the two integrals here separately, because really that's the idea right there. Let's consider each one of these as two separate problems. And once they're all successfully giving us a finite value on each one of them, then we can say this final integral from minus infinity to positive infinity will equal to the sum of these. Okay? And so in that way, now I'm going to erase the definition on my board here, even though sadly I didn't put it up that long yet. I haven't had it here on the board long enough. All right, so now I am going to start out with that interval from minus infinity to 0 on the same function, minus 7x squared plus 6x plus 4. Okay, and so now just like what in the experience we have learned throughout the earlier problems, then this integral here for this particular form of the improper integral, then we are going to produce the following. We want to consider an integral, a definite integral from an arbitrary t value to 0. So t must be somewhere less than 0. And then on the function negative, 7x squared plus 6x plus 4. But then on this definite integral, once we're finished, we're going to have to find the limits by letting t approach negative infinity. Okay? And so if we're completely, aside from being a limit problem, if we're completely regarding this problem as a definite integral problem, then fundamental theorem of calculus says we can just first find the antiderivative of that, which gives me 7/3 x cubed plus and 6x now square over 2, so that makes it 3x squared plus, and now it's going to be a 4x. Okay, it's a polynomial again for being the antiderivative of our current function there, and then we need to evaluate this from t to 0, and then on top of that, this problem of ours must be a problem where we're letting t approaching minus infinity. Okay, and then being a polynomial, now each term here has a 0, so substituting 0 into this, the upper limit of our integral problems here, of our arbitrary definite integral here, is going to be a 0. That upper limit substituted it into the antiderivative. So that means we're looking at r is 0 out, okay, subtract, and now I have a polynomial minus 7/3 t cubed plus 3t squared plus 4t. Okay, and then overall it must be a limit problem as t approaching negative infinity. Okay, and then I'm running a little short in space, so allow me to erase this quick step right here and use that for my next step down right here. So in the next step down, it's going to become, we're just simply going to distribute the sign, the negative sign here, and then with that 0 part right there, it's completely gone. So we now have remains with a polynomial completely in terms of t right here, and we're letting our t variable approach a negative infinity. And so in that way, it's going to be a positive 7/3 t cubed minus 3t squared, okay, and minus 4t. All right. And so now we have brought ourselves down to a very simple problem where we're approaching t to negative infinity and on a polynomial like this. So it's a polynomial, and just a quick reminder of calculus 1 material, but this function here is a polynomial of degree 3, and then it's a positive leading coefficient. Degree 3 here is an odd degree, right, and positive leading coefficient. So that means the left-hand behavior has to be, I don't care what's going on in the middle, but this function has to have a graph that has right-hand points up and left-hand points down right here. So that quickly allows me to say that this limit here is a negative infinity. Okay, it's a negative infinity. And so that means this integral itself here is immediately and I don't even have to find the answer to that because there isn't an answer. Okay, and so this piece right here is a divergent one. Okay, this piece right here is a divergent one. Now what it means consequently is, let me move over to the other board. See, as I said earlier, having an equal sign here is a little bit dangerous, but we can treat that as a sort of like we putting an equal sign here to bring up for us a plan that, hey, tentatively we want this integral to equal the finite limit on both of these. But recall from the definition, we need both of these to come to, we need both of these two improper integrals to come to finite values. But we have already proven that this one right here just now on the other board, this one is already a divergent one. Okay, so as long as one of the two here is a divergent one. And so now I can make my ultimate answer over here. We can't even have this equal sign right here. So now here's what I'm saying. Now I have to, okay? I simply erase to make space, but that's, so after all the work we have done here, there's no need to move on to the other improper integral, but now I can make that final conclusion immediately. This overall integral from minus infinity to infinity on minus 7x squared plus 6x plus 4. This improper integral is a divergent one. All right. And now in the way, in the logic, in the part of the logic where it's being stated in the wording of the problem right here, then we came to divergent one. And so that means we stop right there, because we only have to evaluate to the final numerical answer when we can say that it's a convergent one. But now in this problem of ours, it's not a convergent one, it's a divergent one. So we can stop the problem right here, because there is not going to be an actual value that turns out for this. Okay, and so that's our final answer for this problem. This integral is a divergent integral. This improper integral is divergent. All right, and so now let's look at another problem. Now I'm looking at part B of our example. All right, so let's write it down. In part B of the example, let's look at an integral from minus infinity to positive infinity. And here I'm looking at x to the fifth e to the minus x to the sixth with a dx. Okay, so that's our improper integral right there of the third form. So now, again, with this overall interval being from sort of like a complete infinite interval from minus infinity to positive infinity right there. Okay, so tentatively I want, and just like the way how many textbooks are saying, tentatively we want this to have the answer that is the sum of the integral from minus infinity to 0 on this function x to the fifth e to the minus x to the sixth, and then add with the answer that comes out from the integral from 0 to infinity of x to the fifth e to the minus x to the sixth dx. So tentatively we want, so this is only an indicator that we want this to happen. Okay, but then in order to get that, we need to consider the work separately. So again, let's start out with one of them first. Really, with picking this one or the other one is pretty much your choice. I choose this one again first. Okay, so allow me to go with that minus infinity to 0, x to the fifth. Let's consider this one separately. E to the minus x to the sixth here dx. Okay. So with this one here as a consideration, here's how it works. I'm gonna start out looking at the limit problem. I'm gonna produce a limit from t to limits problem on t approaching negative infinity, where our arbitrary definite integral now is from t to 0 on the function x to the fifth times e to the minus x to the sixth dx. Okay, and so now I'm gonna need to move over to the other board. Feel free to pause the video to copy down the problem if you need. Okay. All right, and so now on this board of mine right here, I can quickly do a substitution for I'm going to substitute u equals how about x minus x to the sixth. Okay, so if u equals minus x to the sixth, then that means du dx will equals minus 6 x to the fifth, and we can arrange this after we've learned about the substitution methods right here. Then we can arrange this as du over minus 6x to the fifth, and all that there equals dx. And so now with this separate out, then with our current integral, again, let me copy it down from the other problem like that. So t to 0, and then x to the fifth. And then I forgot one more line right here. Now when x equals t, then we're looking at the lower u is going to be minus t to the sixth, and the upper u is going to be 0. So with this current problem, x to the fifth did not get a substitution, e to the minus 6. So this is now u, and then dx in our previous step now becomes du over minus 6x to the fifth. The lower bound here for the integral is a minus t to the sixth, and the upper limit here is a 0. Okay, and then we're still going to take the limits of this integral problem to let x approach negative infinity. Okay, and so now let t approaching negative infinity. And so the x to the fifth here can cancel, and we can also bring that minus 1/6 to the front here. Now I cancel that, and so this is now entirely an integral problem that we're advancing with the substitution method. So minus t to the sixth to 0, and here it is e to the u du. And I forgot to mention that I should have had a negative 1/6 here, negative t to the sixth to 0. Okay, so that's how our integral has become at this point completely in terms of u right there. All right, and so now this limits t goes to negative infinity. Now fundamental theorem of calculus comes in and say we take the antiderivative, so that becomes e to the u, and we need to evaluate this. So there's a negative 1/6 in front, and we need to evaluate this at minus t to the sixth to 0 right there. Okay. E to the u, should realize that. All right, and so further I'm going to evaluate our antiderivative at these two integral limits right here. One of them is 0, the other one, the lower one, is negative t to the sixth. And so I'm looking at minus 1/6 times e to the 0 minus, okay, and then there is a negative 1/6 times e to the negative t to the sixth power. Okay, and then this overall problem is regarded as a limit problem where we're letting t approaching negative infinity. Okay, and so in the next step, so that first term is a negative 1/6. The next term here, to get the two negative sign after removing the parentheses, becomes plus 1/6 with e to the minus t to the sixth power, and overall this is a limits problem where we're letting t approach negative infinity. Okay, and so now as t goes to negative infinity, then the t to the sixth will always become a positive. The t to the sixth right here in the problem will always become a positive infinity. But now overall it's a negative because of due to that negative sign, the e to the negative t to the sixth term here will vanish down to a 0. So this whole term here go to 0. So my overall limit here will become a negative 1/6. Okay, and so if you would like a detail, if anyone viewing this video would like a detailed explanation of how I had this whole term go to a 0, then you can either view my video lesson on taking limit at infinity, or you can find a way to get a hold of me, and provided that you are a student of mine right there. Okay, but so now it says that we come to a finite value. This value here on this particular limit problem is finite. Okay, or in other words, the separate infinite, this separate improper integral has a convergent answer right here, or it is convergent. It is a convergent improper integral. So in that way, now I can even say that I can make my conclusion that. So as a conclusion, we don't need to say it's convergent, but I'm just saying that this answer here, this has an answer being a negative 1/6. So we had one answer. Okay? And so, just like that, we're going to have to do another work for that improper integral right here. So two separate improper integral works right here that need to be done. So we have found one of them. And so now I'm going to start getting on 0 to that improper integral from 0 to infinity. X to the 5th, e to the minus x to the 6th. Okay, and so with this integral, it is the plan for that. Okay, that's why I'm using colons here. The plan for that here is that it's go from, think about an arbitrary definite integral from 0 to t. Okay, x to the 5th, e to the minus x to the 6th dx. Okay, but in the end, we're letting t approach positive infinity. Okay, and so now in that way, and seeing this completely as a brand new problem, a brand new improper integral problem for us, then I'm going to do another substitution. And the structure of the problem is mostly the same as the previous one, the previous part of that. And so here I'm going to let u equals minus x to the 6th. Okay, and then so that means my du dx is going to be minus 6x to the 5th, or in other words, we can rearrange this as a du over minus 6x to the 5th to equal dx. And then the lower limits u1 is going to become, now if u equals to the minus x to the 6th, then the lower limit of our currently arbitrary integral is going to be this 0 right here, this lower limit. So in terms of the variable u, then u1 is going to be 0 to the 6th, actually minus 0 to the 6th, and that gives me 0. Okay, and for u2, the upper limit, it is going to be minus, and then t to the 6th, and that gives me minus t to the 6th. Okay, so we have lower and upper limits in terms of the variable u now, in respect to the variable u. So that means our starting integral that was from here now becomes an integral from 0 to minus t to the 6th. Okay, but it's x to the 5th did not get a substitution for that, so we leave it there. E to the x to the minus x to the 6th, but minus x to the 6th is a u according to this substitution. So now it's going to be a u here, and then the dx is a du over minus 6x to the 5th, just like that one here. All right, so now I'm going to go ahead and cancel out the x to the 5th and pull the negative 1/6 in front. But by the way, right now it's a limit problem as t is going to positive infinity. Okay, and so in my next step, I can write this as a negative 1/6 integral of e to the u du, where we're integrating from 0 to minus t to the 6th. Okay, and here we're letting t approaching positive infinity. All right, so a couple more steps right here waiting for us. So now I can just take the antiderivative of e to the u right now. So that gives me e to the u with negative 1/6. That's the antiderivative. And then I am going to evaluate from 0 to minus t to the 6th. And yes, this problem in the end will become a limit problem by taking t to positive infinity. Okay, and so now I'm going to keep continuing here. So minus 1/6 e to the, so now u gets substituted by minus t to the 6th. So it becomes minus 1/6 e to the minus t to the 6th. Okay, and then I'm going to subtract, and then now I'm looking at negative 1/6 e to the 0, and then I'm taking this limit, okay, as I let t approach positive infinity. Okay, and this term here is, so it's e to the 0 is a 1 with minus a negative 1/6 times 1, so it's going to be it's a plus 1/6 here, it's plus 1/6. Okay, and then here I'm looking at and so that first term here is a negative 1/6 e to the negative t to the 6. And so with this final expression completely in terms of t now, then I am ready to find that final limits letting t approach the positive infinity. And so again, with our understanding from calculus 1 right there, then this overall term will go to 0 as we're approaching that t, as we're letting t approach a positive infinity. So the overall answer here is going to be a 1/6 as well. Okay, the overall answer there is going to be a 1/6. And so now that on this board, it means that this improper integral that we plan to find the answer as that we worked out as a limit problem on this particular limit on the arbitrary definite integral from 0 to t here. This particular limit here is a positive 1/6. Or that means further, now we found earlier that this piece of the improper integral was already a convergent one. And so just now here's another tremendous result that we now know. That this integral now, this improper integral now is convergent. So tentatively, the definition said as long as we can find and prove both of these improper integrals to be convergent, then this answer will be. So we wrote this down. We wrote this down only as a beginning, in the beginning, as a plan that we want that sum to happen. And now we have all that tools. We have all that enough reasoning to say that now the answer can be just simply the answer from the earlier one plus with the answer here that we've just now found. So logically speaking, at this point, first of all, the problem says determine whether this integral is convergent or not. Both of these integrals, both of these little improper integrals are now convergent. So now my first statement here, conclusion here, is to say this integral from minus infinity to infinity, from x to the fifth e to the minus x to the fifth, okay, is convergent. That's the first thing. And now according to the way how the problem is saying, now once we know it's convergent, then the next step, so I'm short of space, so I'll have to erase this line and saying, but the line I'm about to say is really just, so I'm going to have to erase this, okay? But once we know that it's convergent, then the step to really evaluate that is to really add up the two answers. So that integral here has a final answer being minus 1/6 that we found from the answer of here, and then add with the positive 1/6 that we've just now found from the work of this particular integral over here, improper integral. And so now the sum of the two answers here come out being 0, which is now our final answer, the evaluated answer of our overall improper integral here from minus infinity to positive infinity. Okay, and that's how a problem like that is being done. All right, and we are now at example 3, where I'm able to bring in a problem that is very popularly written in many textbooks, standard calculus textbooks out there. Okay, so the problem is as follows, and it's popular on its own because it has its specialty that deserves people's attention right there. And I will discuss about how special the problem is and what impact it will do for us after we finish with the problem. Okay, but now allow me to introduce the problem here. So for example 3 right here, let me write it down. The example 3 the wording of the example 3 is asking the following. Let's say for which values of p is the integral. It's the integral. So now here's my integral. It's an integral from 1 to infinity, okay, on the function 1 over x to the p. Okay, so that improper integral of the form we have seen earlier, that was actually, form 1 that we have seen from the definition, part B of the definition we have seen earlier. Okay, so we basically, the question want to find out for which values of the p parameter here that makes this integral convergent. Okay, that's the part of the main part of the question right there. So we want to find out which values of this p right here. So the x here is the variable of the integral of the function in the integral, but then the function in the integral also depends a little bit on that parameter p given right here. And right now I see that as a power, the power of the x in the denominator, in the structure of how it looks like. Okay, so quickly and you can see that the question specifically asks for which values of p making the integral here convergent, but you have to think broader in the sense of the impact, the consequence here, that once we found all of those values making this integral convergent, and that also means outside of those values we have found for p, those will also be the one that making the integral divergent. Okay, so sort of like one word, but we can answer all of those. So the question is specifically looking for values of p that making this integral convergent, but it also means that outside of those p values we found previously, it will be the one that making this integral divergent. Okay, so now before I get started particularly, let's observe this function a little bit. It's a 1 over x to the p, and as I have mentioned already, that 1 over x to the p is sort of like so x here is to a power p in the denominator. So think about specifically, there's something that we already know commonly right here. Think about if p, and this is by far just a scratch work right there. If p is 1, then this function is 1 over x. Okay, the common function 1 over x function, which is, it falls right into the case where if we're taking the antiderivative of this, we have to go through the natural log function according to the antiderivative rules we have already learned. Okay, and so that's why this specific case right here worth our attention to consider that separately. So now I'm going to erase this. Okay, and let's move over to my other board right there. Okay, so now I'm going to specifically consider that individual case where p equals 1. So if p equals 1, then again the integral, this integral right here, 1 to infinity of 1 over x dx, this integral will be equal to just the integral from 1 to infinity of 1 over x function. It's the 1 over x function. And then, so once we had that laid down right here, then again, just like how we have been handling this function right here, then we have to start out by considering the limits problem by letting t approach positive infinity. And our function, our arbitrary definite integral here happens from 1 to t, where t is an arbitrary value above 1 right there. And then our function is 1 over x. Okay, and so now at this point we are ready for using the fundamental theorem of calculus. So here it gives me the natural log of x in absolute value, and then we need to evaluate this from 1 to t. Okay, and then on top of that we have to treat the problem as a limit problem by letting t approach positive infinity. And so continuing further with the fundamental theorem of calculus, then in the next step I am going to evaluate this antiderivative of our 1 over x function. Okay, and that's why it's special. We need to treat this case a little bit specially right here because it stands on its own. It's not just the usual power rule. Okay, because I mentioned about power earlier, but here's one specific case where we cannot use the power rule. So let's consider that separately. Okay, and so now continuing with the fundamental theorem of calculus, I am going to substitute t into my x right here. So I have natural log of t minus natural log of 1 in absolute value. And then with that expression, which is clearly an expression completely in terms of t. And now I'm going to go ahead and we're more firm that the problem here is an expression that gives us an expression in terms of t, and we're taking limit as t approach positive infinity. Okay, and so now all of that here, all of that there, you can see that, well, that term here, according to the property of logarithm, is always a 0. So in the next step, just a small little step right here, it means we're trying to find the limit of the function natural log of t as t approaching positive infinity. Okay, and so we have seen this problem all over calculus 1. So there are many different ways to put our reasoning, but the answer for this is going to be a positive infinity. Okay, and I can quickly explain graphically that the graph for the natural log function in general is a rising graph. It rises slowly, but in the end it's still rising and rising without a bound right there. So that's why as t is getting to positive infinity, right, as the main variable is getting to positive infinity, the function for natural log keep rising vertically. And that's why the answer for this is a positive infinity. Okay, so positive infinity is the answer of the limits problem. But that now means further, that this integral, so now I'm ready to erase this part of the board to make my conclusion. My conclusion now says it's now legal for me to make that conclusion that this integral, improper integral from 1 to infinity of the function 1 over x dx right here. This integral in particular is divergent. Okay, so this is just a standard problem that we determine divergent or convergent of an integral, of an improper integral. But now that is enough to nail down one case actually. So back to the problem itself, the problem of the example 3 here. Then for which values of p is this integral convergent? But we found so far that, hey, when p equals 1, this integral is not convergent, divergent indeed. So it's worth to summarize it down. So now I can say clearly that specifically this integral, okay, this integral from 1 over infinity of the function generally in the form 1 over x to the p dx, okay, is divergent. Okay, or how about, let me write it for short here, how about diverges for p is exactly equal to 1. That's one case we nailed down so far. Okay, and then so and for now it's just a quick summary chart right there, and I will get back once we completely build that summary chart right here, we're going to make a final statements about what values in general of p will make this integral convergence, okay, and otherwise. Okay, but now after we particularly focused on p equals 1 right here, then that actually kind of gave us an advantage, because it narrowed down our attention to other cases. So why don't we just now, from this point right here, why don't we consider the case where p is greater than 1 and the case where p is less than 1. Okay, and so now that means we have a more clear picture of where to go from here. So now there's the next case I'm about to consider. All right, so if p is greater than 1, let's see what happened. Let's specifically consider that case right here. And then I will keep bringing in minor details as we go along. Okay, so the problem is, at start, is an integral from 1 to infinity of 1 over x to the p. Okay, that integral right here, and we want to find out is if this is going to be convergent or divergent. Okay, and so now with this case specifically for for p being greater than 1, then to consider this, then I am going to produce the limits. Okay, so for the limits from 1 to t of the function 1 over x to the p dx. And notice the advantage of p greater than 1 now is that now we can see this completely as we can see this completely as an x to the minus p power, and I will get to that later. Okay, and the power rule will eventually be very applicable here, and that's why it's worth it to pay separate attention on the case where p is positive, greater than 1. Okay, and where it was earlier and where p was equal to 1, and we had to treat that as a logarithm when we take antiderivative. But now let's save that for later. In the end, this arbitrary integral from 1 to t right here, we need to, on this arbitrary definite integral from 1 to t, we need to take the limits letting t approach positive infinity. Okay, and then, so now that means, back to what I was in the middle of saying earlier, so now realizing that we can use a power rule for that. So the first thing here, before taking antiderivative, I'm going to rewrite that 1 over x to the p as x to the minus p power. Okay, and then the integral here is from 1 to an arbitrary t value, and then we're allowing t to approach positive infinity. Okay, and so that means further that my antiderivative, and according to the fundamental theorem of calculus, we need to find antiderivative first. So that gives me x to the minus p plus 1 over negative p plus 1. And then we will evaluate this from 1 to t. Okay, and then of course once we finish evaluating this problem, t value will be taken as a limit to positive infinity. Okay, and so now with the fundamental theorem of calculus, it's the next step here, we're going to substitute these two values into the function. So now what I see in the next step here, for t to positive infinity, then now allow me to write this part right here in the denominator as a separate fraction. So how about 1 over minus p plus 1 times t now, so because we substituted t for x, so t raised to the power negative p plus 1. Okay, and then I'm going to subtract, and then now I'm looking at 1 to the negative p plus 1 power over minus p plus 1. So that's the expression that happened that we run into after we have successfully substituted in t and 1, okay, for our antiderivative. All right, and so now this term is nothing but just 1 to the minus p plus 1 power. So I can write this, or I can wait that for the next step. But let's give some explanation about the minus p plus 1 a little bit. Okay, now we know that we're currently considering the case where p is greater than 1. So p is greater than 1 means it means logically the same as we can subtract p from both sides and leaving a 0 greater than minus p plus 1. But see, writing 0 greater than minus p plus 1 is the same as saying that minus p plus 1 is less than 0, a negative value. There's a reason why I mentioned this. Minus p plus 1 is a negative value, means this power minus p plus 1 is a negative power. And so with being a negative power, I can take advantage and use some algebra on that in the following step. So that means first term here becomes 1 over minus p plus 1, but times 1 over t to the now p minus 1. Okay, so when we turn that into the reciprocal, then that power becomes the opposite power in the denominator. That's why it's instead of minus p plus 1, now it's going to be p minus 1. Okay, these are the opposites of each other. But now the t is in the denominator. Okay, and now the p minus 1 here, that also means further that, so from this we also imply that p minus 1, see, p minus 1 subtracting the 1 over has to be positive. And that's why it's in that form right here. So now I can see that we have a 1 over t to a positive power in the denominator. And then I'm going to subtract 1 over minus p plus 1 as the next term. Okay, and this work here is a work surprisingly that is dependent on the variable t. Now all of the minus p plus 1 other things that involve with the p right here, they're actually, this is a constant coefficient, and this is a constant term right there. Okay, so this is the only part where it's dependent on the t right there, and that's the part where it's dependent, that's the limit will drive to different value. And so now overall this is an expression in terms of the t expression, in terms of the t variable. So I am going to take the limit as t going to positive infinity. So now that means my final answer here, now if we observe this a little more carefully, then so as t goes to positive infinity, then that whole term here will go to 0. So in my, I have video lesson that teaches how to find limits here, and that has detailed explanation of why something like this go to 0 like that. So find that other video lesson, and besides, anyone viewing this video lesson is required to be the past calculus 1 already. So you should be able to quickly find out why this is going to 0 as we take t approaching positive infinity. Okay, so 0 times with that coefficient give me a 0 in the first term. And then limit law says, that constant terms remain the same. So minus 1 over minus p plus 1. And so minus 1 over minus p plus 1 is actually the same as just 1 over p minus 1. Okay, 1 over p minus 1. And so here's the result. This is supposedly a finite value. It's independent from the t variable now. And it's just once we know what our p value is given in the beginning, then the final limits here will turn out into that value. It's a rule of thumb like that. So that means, so now I'm seeing that I have a finite value. So when p is greater than 1, this limit turns out to have a finite value. Having a finite value means, I'm short of space here, so I'm going to quickly erase this board. Once we've just now proven that limits at infinity turn out to have a finite limit, then now that means I'm saying that, and I have to leave this answer, I'm saying that this integral here of that form is convergent. Okay, it's convergent. And further we found in the case of convergent, then just like the usual work we have seen back in example 1 and example 2, after deciding if an improper integral being convergent or divergent, once it's convergent, known to be convergent, then we can proceed to evaluate it. So that means this integral from 1 to positive infinity of 1 over xp, okay, is equal to the answer 1 over p minus 1. Okay, and so now it's worth our attention to nail this case down into that summary chart right here. All right, so now the integral from 1 to infinity of 1 over x to the p, okay, will converge, okay, or we can say converges for p being greater than 1, okay, and further, we also found out that, so right now I'm just summarizing things, that integral in that case right there, just for that case when p is greater than 1, then this answer is 1 over p minus 1. Okay, and so now we have one more case remains. So earlier I looked at what happens when p equals 1, and we found out that the integral here diverges. Just now we found out that generally when p is a value, is a power that's above 1, greater than 1, then this integral is convergent. So now what happens when p is less than 1? Okay, so let's find out. All right, so if p is less than 1, and again the integral from 1 to infinity of the function 1 over x to the p, okay, so this function here, this integral here, first of all, to consider that function, then I'm going to produce the limits on an arbitrary definite integral from 1 to a t, 1 over x to the p, okay, and then allow t to go to positive infinity. Okay, but keep in mind this time here we're considering considering especially that case where p is less than 1. Okay, and so now with this limit, yes, in the end, well, in the case here, in this specific case, p is less than 1, but it's not 1, so we can still treat the problem as using the power rule. So my point now is that we can rewrite this function 1 over x to the p as an x to the minus p power, okay, and then finding the integral from 1 to t, and then the integral will take the limit as t approaching positive infinity. Okay, and so now just the usual work again. First thing, I'm going to find the antiderivative of x to the minus p, which gives me x to the minus p plus 1 over minus p plus 1. Okay, and then we're supposed to evaluate this from 1 to t, but then we have to take the limit as t approaches positive infinity. Okay, and so now, and then in the next step, it means I'm going to have to write that as a 1 over minus p plus 1 times t substituted for x raised to the power of minus p plus 1. Okay, and then minus, and here when we're substituting 1 into the place for x, we're looking at minus 1 okay, over minus p plus 1. Okay, and then overall this is a problem that's now dependent on t. I'm going to take the limit as t approaches positive infinity. Okay, and then very similar to that, the earlier step. So t to the minus p plus 1 power, but let's look a little closer into this form, this power form, like the minus p plus 1. Now p is less than 1, but that means minus p plus 1. How about let's write it this way. I'm going to subtract p to the other side, and that means I'm going to lead to having 1 minus p is greater than 0. Okay, but 1 minus p is the same as minus p plus 1. It's a different way of writing that. So that means I have just now proven that minus p plus 1 is a quantity that is positive. And now specifically for this power, it's a positive power. Okay, so now when you're taking, and so again, this particular term is a constant term. So limit law says, well, you know, anytime we're taking limits on a constant term, it remains the same. So that terms remain the same, but this term here will always grow to positive infinity because see, think of that as a power function or as a polynomial over here with degrees minus p plus 1. Okay, because it's a positive power now, so we treat that as like a polynomial. So in the end, this overall limit here turns into a positive infinity. So the limit turns out positive infinity. That means the integral here. Okay, so now I can erase this work and make my final conclusion that this work now is this integral now is divergent. And so, and now back to the kind of logic that we have seen back in example 1 or example 2. Then anytime we have proven an improper integral being divergent, then we no longer need to continue to evaluating the problem. We can just stop right here. But now that is enough. That is another case that worth our attention to put that into the summary chart right here. Okay, so into that summary that we have found right here, then this same integral. So now we track down the third case, the integral from 1 to infinity for 1 over x to the p. Okay, will diverge, or I can say diverges, okay, for p being less than 1. And so for any time it's divergent, we don't need to find the final evaluated value. All right, and so in that way, now finally concluding the whole problem. And I've had this here long enough, so now let me erase out this summary. We can put it away. So 3 cases together, we can see that when p equals 1 and when p is less than 1 that we have had just earlier, then this integral specifically will diverge. Only in the case where the value of p is positive, then the interval here will be convergent. So now we are ready to make into make it into a, to formulate into our final answer. So as far as the direct answer of this question, then I'm saying, okay, this integral 1 to infinity of 1 over x to the p, okay, that integral is convergent, okay, is convergent. That's a direct answer for p greater than 1, okay? And then in that case where once we've had that, the value for this integral itself, because remember, anytime that we can prove that an improper integral is convergent, then we can proceed all the way to the end to find its final numerical answer. So 1 over x to the p has an answer numerically 1 over p minus 1. Okay, 1 over p minus 1. That's one case. And now as the other part of the answer that came out consequently, then I can also conclude that this integral from 1 to infinity, the function 1 over x to the p, okay, is a divergent, okay, for any value of p less than or equal. So we also including that case where the value of p equals 1, so less than or equal 1. And so in this case we don't need to worry about the final numerical value of that. Okay, and so now before I'm completely done with this particular example right here, I talked a little bit about this particular problem. This particular integral here has its own specialty that deserves people's attention. So what is that specialty? I mean, not just about the form here, but you will be surprised how many times you see this problem out there. Okay, so now let me bring into your attention a couple of problems right here. You will be sometimes here and there see a problem as following: 1 to infinity, for example, with 1 over square root of x. Okay, so now once you are given an answer like this, and a lot of times in a case where you don't have time to sit down and formally go through the math, you already have a quick answer to determine whether this one here is convergent or divergent. Okay, I can now tell immediately without producing the limits problem and all that. Why is that? Because this function here now, what I recognize is it's a 1 over x to the 1/2. Just the function itself is a 1 over x to the 1/2. Okay, and so as a complete integral from 1 to infinity. But see, so p here in this case is 1/2. So that value of p falls into this case where the integral will be convergent. That's how I know immediately that this integral will diverge. Okay, so and maybe I accidentally said convergent earlier, but so when p is less than 1, which is this case, and I know that this integral here, this improper integral has to be divergent. Okay, so it saves me completely all of that effort to go through the limits, producing the limits problem and get it done. Nope, that we can have a way to quickly determine that. Okay, and be ready that there will be problems out there here and where it asks you to just quickly determine whether a given integral, a given improper integral is to be convergent or divergent without producing the limits work. That's one part of, this will put into your usefulness, understanding that how you can quickly decide on some of the problems there. Okay, and then there are other problems out there where you can look at integral from 1, okay, to infinity of 1 over x to the, okay, how about 3/2 power, okay, dx. And usually it's even written in a more complicated form, like something like this: 1 over x times square root of x in the denominator. So at first, when we look at something like this, it seems like we have no clue to determine if it's convergent or divergent. Okay, but now, and think about when you're in that situation where you are either asked to decide a convergence or divergence on this integral without setting up the limits problem, or you may be in a rush situation where you are not able to carry out the formal limits problem. Then you can see that this x to the square root x, x times square root x right here is the same as a 1 over x to the 3/2 power. Okay? And so now this is your value for p right here. P equals 3/2, which is the value of p, where it's greater than 1. And anytime the value of p is greater than 1, this integral will be convergent. Okay? And be convergent, that means, and so now I can say that this integral, okay, so our quick statement here is saying this integral is convergent. Allow me to use a shorthand writing CONV for convergent. And being convergent, we can even one step further. That it's convergent and its final value will come out. Okay, the final value for this will come out being 1 over, now our value of p is 3/2, so it's 3/2 minus 1 in the denominator. Okay, which is a 2. All right. And so that's how, that's how this type of integral right here, this improper integral is very deserving your attention. Okay? All right, and so now at this point, we are ready to classify, because I've said earlier that eventually I'm going to put all of the forms here into a particular classification here. So you have seen enough up to this point to put all of the forms of the improper integrals we have learned so far into one particular recognizable form right here. Okay, so let's look back at the one that we started our lecture here. So the first form I introduced was an integral on a function where we are accumulating from a finite value to infinity. Okay, and then so what I know here, what I see here is that this integral, the interval that we're integrating over is an infinite, is over an infinite interval. Okay, and after that form, I introduced you to the second form where we were integrating over an interval from minus infinity to a finite value, okay, on a continuous function, and assuming that, and we put ourselves in a case where the function f of x here is continuous over any of those integration interval. And so this is another interval where the integration interval is also another infinite interval. Okay? And the one that we just recently finished was this integral over a complete, an interval that's completely infinite right here, minus infinity to positive infinity on a function f of x in respect to x. And this is another problem where we consider the integration interval is an infinite interval. Okay, and so yes, that's the common property we recognize in these three forms of the improper integrals. And as a matter of fact, this last form here, this third form where I introduced just most recently right here, the part of its work right here require both of these that we learned, prior to that. And so these three forms of the integral, of the improper integral, we refer to these as yes, they are the improper integral. Okay, improper integral these are improper integrals of so now the term here, okay, type 1. All right, so now it's a very common term that I'm using here. Many textbooks, many mathematicians, many textbook authors, many professors out there are using the same term right here. It's improper integral of type 1. And what it means here, it's an improper integral where the interval of integration is an infinite interval. Okay, and that's what improper integral of type 1 is all about. All right.